Hello everyone, welcome to week 9. We're now going to shift things up a little bit and start looking at conditionals. So we've already seen the Boolean operators and ignoring ought, and we can construe conditionals in terms of these, but we might want to just have a ready symbol for if then and if and only if. We're going to start this off by looking at the material conditional, which is just the if then of our language. Let's start things off by having a look at the truth table for the material conditional. Here, if P then Q, which is how we'll read this arrow, is true when P and Q are both true, and it's false when we go from T to F, when P is true and Q is false. It's true when P is false and Q is true, and it's true when both are true. In this way, the truth table for if P then Q is actually identical with the truth table for not P or Q. So we don't need the arrow, but it's logically interesting and we can use it as an abbreviation of not P or Q. Now let's look at some natural language equivalences. So it's straightforwardly equivalent with if P then Q. It's also equivalent with Q if P and P only if Q. We're going to have a look at these in just a minute. And finally, it's equivalent with provided that P, Q. So take for instance a natural language sentence like, if the skis fit, then you can use them. We can go down to our next one here and say, you can use the skis if they fit. We can further say, you can use the skis only if they fit, and provided that the skis fit, you can use them. Now, these two middle ones here cause a good deal of confusion, and it's worth taking a bit of time to zero in on them and see why we take both of these to be equivalent with if P then Q. The way to do this is to think about them in terms of necessary conditions and sufficient conditions. A necessary condition for something must be met, whereas a sufficient condition doesn't necessarily need to be met, but if it's met, it's condition enough for the thing. This might seem a little bit out there, so let's look at an example. Take completing homework as a necessary condition for doing well in the course. You're only ever going to do well in the course if you complete the homework. It's a necessary condition. On the other hand, completing the homework isn't a sufficient condition for doing well in the course. Just because you complete it all doesn't mean you'll do well. So completing your homework is a necessary condition for doing well. It must be met, but it's not condition enough. On its own, it doesn't guarantee that you'll do well in the course. Consider an example of a sufficient condition that isn't necessary. Suppose that we're building a house. It's a sufficient condition for erecting the walls that they be made out of brick, but it's not necessary. We could make them out of wood instead. So it's condition enough that the walls be made out of brick for them to exist, but you don't have to make them out of brick. It's not a necessary condition. So this condition is sufficient but not necessary. Turning back to our language of conditionals, we can see that only if introduces a necessary condition. You do well in the course only if you complete the homework. Conversely, if introduces a sufficient condition, and if I said to you, you'll do well in the course if you do the homework, then what I'm telling you is that this is a pretty easy course. This is why we write only if as P arrow Q and if as Q arrow P. There's a pretty easy way to remember the distinction between only if, and it'll come up when we deal with the biconditional, which we read as if and only if. So we'll talk about that in the next video. For now, I want to just conclude with a quick discussion of the meaning of unless. How do we read P unless Q? Well, think of an example in our blocks language. How do we read this? In a way, it works something like if not, as we can see from this example. Since every object here will be either a cube, a dodecahedron, or a tetrahedron, we would say if it's not a cube, then it's a dodecahedron or a tetrahedron. So these are all equivalent. If we want to write this out symbolically, then we already have the answer based on our if not. So we'll do not, copy cube A, arrow. That's our then. So in general, P unless Q is to be read as if not P, then Q. I'm going to write this up here just to make this clear. Anytime you come across unless, it's helpful to just think to yourself, if not. Now, I want to make one final remark here about unless that might be a little bit puzzling, but it's worth noting now, because I think that at least some people will say, wait a minute, if P then Q is equivalent with not P or Q, and P unless Q is equivalent with if not P then Q, which gives us the following truth table, then it seems as though if not P then Q is just the same as not P or Q, which, as we can see, will be the same as the truth table for P or Q, since the two nots cancel out. And the truth of the matter is that these are equivalent, and we'll be discussing this in greater detail later on. I'm merely flagging it now just to say, if this strikes you as interesting, that P unless Q just has the same truth conditions as P or Q, you're not wrong, and you're thinking on the right track. But again, this is something we'll explore in greater detail later on. Now I want to do one final thing here. I know I said this was going to be final, but I have one final thing, which is to call attention to the material conditional as it appears right here, where it's true if it goes from true to true, true if it goes from false to true, true if it goes from false to false, but false if it goes from true to false. And I expect that this will strike at least some of you as quite obviously linked to the notion of logical consequence, where the premises entail the conclusion just in case we never go from T to F. So T to T is fine, F to T is fine, and F to F is fine, but T to F is not. And in fact, the two are very closely linked, and we can reduce our notion of logical consequence. Let's see how we can do this. So recall that on our definition of logical consequence, the premises entail the conclusion so long as we can't go from a true set of premises to a false conclusion. But of course, false to false is fine, and false to true is fine, and certainly true to true is fine. So on the material conditional, if P then Q will hold so long as P isn't true where Q is false on our truth table. So the two notions are quite similar, and indeed we can say that Q is a logical consequence of a string of premises, a conjunctive string of premises P1 through Pn, if and only if P1 through Pn then Q is a logical truth. This is just to say that if you were to take this sentence, if P1 through Pn then Q, and put it into a truth table, then the column under our main connective here would contain only T's. And that's just how we can reduce our notion of logical consequence to the material conditional using our notion of logical truth.